Hello. Okay, so what we're doing is we're going to talk in this video about oxidation numbers. Okay. Um, this isn't too terrible. It's just kind of fancy counting, and we'll get ourselves into it and used to it as we go. Okay. What we're looking at here is this is a bookkeeping method for keeping track of electrons, and this is going to be very helpful for us when we think about um, redox reactions, which is where we're headed into with this bit now anyway, okay? Because we need to keep track of where the electrons are. Okay, our official definition here is that this is a hypothetical charge on an atom that it would have if all of electrons were assigned to the more electronegative atoms, which is, kind of weird. Um, this can happen in solution or not in solution. So as we work through these reactions, we're going to see things that are aqueous, solid, liquid, gas. We can always figure out what the oxidation numbers are based off of these things. Um, and it's really just some kind of rule-y guideline things. I'm going to try not to do too many exceptions just because the rules make sense and there's a rule for everything. So it's not really an exception, it's just a weird rule. Okay. Uh, let's see where we are now. Okay. So our first thing is an atom that's in a free element is going to be 0. So what do we mean by a free element? Something loose on its own. Maybe it's iron solid, maybe it's oxygen gas, chlorine gas, some sort of elemental form. Ozone is another elemental form of oxygen, so that's also going to be 0. Um, so yeah, anything that's the element loose on its own. If it's something, right, like so iron 2 plus, this guy looks like an element loose on its own, but it's an ion, so not 0. Okay, I'm even going to erase this so we don't ever see it again. Haha, bye-bye. Haha, screw it. Okay. Um, right, so any element loose on its own is 0. It doesn't matter what the element is as long as it's just the free element on its own. Okay. Uh, okay. Damn it, it's doing that thing again. Okay. Now, this is where we get into ions. So if we have um, a monatomic ion, so what that means is the single atom that has an ion. So my other example, iron 2 plus, right, we could have aluminum 3 plus, right, Cl minus, these kind of things. If it's a single atom that has a charge, it is the oxidation number or oxidation state. Oxidation state and oxidation number are the same thing, so don't stress about it. Are the same thing. So iron 2 plus has an oxidation number of 2 plus. Sometimes I'll say this as plus 2 just to kind of keep things a little bit different. Aluminum would be plus 3. Chloride with a -1 should be -1. Barium should be 2 plus. Okay. If it's in a compound, say we have lithium bromide, right? This is not elements loose on its own, it's in a compound. We can figure out what the charges on the things are because it's an ionic compound, right? Lithium in group 1 has to be +1, bromide then has to be -1. Okay, so if we see something like, say we have KMNO4, well, the MNO4 part we're going to learn how to do it in this video, but for right now, we don't know. We know potassium being in group 1 has to be +1. Okay, that means the rest of this, the MnO4, has to be -1, and then we'll work our way through that as we see some other stuff. Okay, so that's if you have a single atom ion. Okay. Now, the rest of these rules are kind of element specific. So oxygen, what we're going to do with oxygen is we're going to assume that oxygen is always -2. There are some cases when it's not, and that's looking out, oh, shit. It's looking out for peroxides and superoxides. These are on the polyatomic ion sheet. Peroxide is O2 2 minus, and superoxide is O2 minus. Okay, which means that the peroxide has an oxidation state of -1, and the superoxide is -0.5. Okay, you will probably know if you have those in there because those are going to be doing the reaction and the oxygens will change. Okay. Most of the time when we're doing these things, oxygen is loose on its own. So, uh, not loose on its own, but it's part of polyatomic ions the whole way through. So if we go back to our MnO4, okay, we can say this guy is +1, and now we know the oxygens are -2. We still have to be able to figure out manganese, and we will learn how to do that as we go. Okay. Um, hydrogen is always going to be +1. And I'm going to say here, watch out for hydrides. And we're probably not going to see it, but I want to throw it at you just so you know. You can point out a hydride based on how the formula is written, right? So typically what we'll see is something like HCl, hydrogen chloride or hydrochloric acid, depending on when H is in the front, +1. You can make compounds where hydrogen has a negative charge. This is the same rule as monatomic ions. It's just we are kind of splitting it apart. This is a hydride because it's minus charged and it's written second. So that's how we know. The calcium has to be +2. So each hydrogen has to be -1. Okay. You will probably not see anything with hydride until we get there in organic at some point. But this is a hydride. It's a hydrogen with a negative charge. Okay. So 99% of the time, you can trust that hydrogen's going to be +1. Okay. Especially if it's written first. If it's anywhere in the formula, like if we have acetic acid and we're trying to figure this out, we can totally still figure it out. These oxygens are going to be -2. All of the hydrogens should be +1. And then based off of this, we'll be able to figure out what carbon is. And I'm going to show you how to do that when we get there. Okay. Halogens. Now, halogens are something that we've always kind of said halogens are weird. Okay. Fluorine is the only one that's not weird. Fluorine is always -1. Okay. And that's the same rule as saying the monatomic ion rule, right? Fluoride by itself is -1. All right. The other guys have options, and this is going to be something we're going to have to tease out as we go, and we're going to see in the next rule how we're going to figure this out. Okay. Typically, halogens can be anything between -1 and +7. Most commonly, the odd numbers are, oops, that's a 2. I want to write 3. The odd numbers are the most common ones, and really, -1 is the most common. Um, but you will see variations on these as we do problems. So we're going to get a rule on how to figure that out. And here's how we can do it. Figure out any oxidation state. And this rule tells us, right, that our total oxidation state on the formula is equal to the total charge on the formula. Okay, let's use one of our earlier examples to test this out. So if we have LIBr, we use this for figuring out the monatomic ion. Sorry, my nose really itches. Um, lithium has a positive charge, bromide then is minus charge. So this has to be +1. But let's say you know this is +1 because lithium is in group 1, but we don't know what the bromide is. Well, our total charge has to equal 0. So this has to equal 0. So the bromide then has to be -1. And this just becomes an algebra problem. Okay. The other one I kept throwing at you was KMNO4, potassium permanganate. You will see MnO4 a lot because it's very um, well used in redox reactions. Okay, so if we break this down, we can look at it. Potassium is in group 1, so it has to be +1. The oxygens have to be -2. There's no charge on the overall formula, so our total, that looks garbagey, our total here has to equal 0. Okay, so what does this mean? This means that +1 plus whatever manganese is, which we don't know, plus 4 times -2, right? Because each oxygen is -2, and there's 4 of them. This has to equal 0. Okay, so 4 times -2 is -8. Okay, so 1 plus manganese -8 equals 0. So manganese is going to have to be 7. Okay, and so this means this is, how did I go backwards? That's interesting. Okay, so that means this has to be +7. Okay, if we look at our, yeah, if we look at our halogen ones that I was doing a minute ago, so things like, let's do ClO4. Okay, ClO4 minus perchlorate. Okay, so here our total is -1. So each oxygen is -2. So the chlorine is, I don't know what, but we have 4 times -2 plus whatever chlorine is has to equal -1. This is -8. So essentially we have chlorine -8 equals -1. So chlorine has to be +7. Okay, you see how we're teasing these out as we go. Let's do another one. Okay, I was so good at not getting that to do it this time. Okay. You guys read? I don't know. Let's do BRO minus. Now let's do BRO2. Okay. So here we have bromite. We don't know what bromine is, so we're going to figure it out. We know each oxygen is -2, and we know our total is -1. Okay. So where are we at? So we can say BR equal, no, BR plus 2 times -2 equals -1. So BR -4 equals -1. So BR equals +3. Okay. Hopefully, we can get to the point where you can do this quickly in your head um, for figuring it out. You'll always have scratch paper to work on and that kind of stuff, so you can do it. Okay. Where's my notes? We can find another example, maybe. No. Okay. Oh yeah, here we go. Let's do. Oh, that's a good one too. Let's do this one. I got room for one more, so we're gonna do one more. Okay, we're gonna do dichromate. Cr2O7 2 minus. Okay, so we don't know what the chromium is. We know oxygen should be -2, and we know our total has to be -2. Okay, so let's set this up like an algebra problem. We have 2 chromiums plus 7 times -2 for the oxygens has to equal -2. So 2 chromiums plus about minus 14 equals -2. So this tells me that 2 chromiums should be 12, which means that 1 chromium should be +6. Okay, we're going to need this skill in the next couple of videos to work on balancing things and figuring things out. So hopefully practice, practice, practice. Okay, if you need anything, you know how to find me, and I will catch up with you later.